When sizing parallel conductors, it's crucial to understand that you cannot simply multiply the ampacities listed in Table 310.16 by the number of parallel sets. A correct method involves several steps to ensure accurate and safe ampacity determination. Firstly, calculate the total ampacity of the conductors. This involves adding together the ampacities of each individual conductor in the parallel set. Secondly, apply the adjustment factor. This is where Table 310.15b2 comes into play. This table provides adjustment factors specifically for various numbers of parallel conductors. For example, if you have two conductors in parallel, the adjustment factor is typically 0.8. For 3 conductors, it's 0.7. With 4 conductors, the factor is 0.6. For a range of 5 to 9 conductors, the adjustment factor is 0.5. When dealing with 10 to 20 conductors, the adjustment comes 0.45. For 21 to 30 conductors, the factor is 0.4. And if you have 31 to 40 conductors, it drops to 0.35. Finally, for an extensive parallel run of 41 to 50 conductors, the adjustment factor is 0.3. To illustrate the use of these adjustment factors, consider a scenario with 3 conductors running in parallel. As mentioned earlier, the adjustment factor for this setup is 0.7. You would multiply the total ampacity of the individual conductors by this factor to get the adjusted ampacity. Thirdly, you have to round down to the nearest standard ampacity. The ampacity value you obtain after applying the adjustment factor might not align perfectly with the standard ampacity listed in Table 310.16. In such cases, you must round down to the closest standard ampacity value to ensure that you are not exceeding the safe operating limits of your conductors. By carefully following these steps, you can accurately determine the ampacity of parallel conductors, ensuring both safety and compliance with electrical codes. It's important to consult the latest version of the National Electrical Code or NEC for the most up-to-date tables and requirements, as codes can change over time. Also remember that other factors, such as ambient temperature and the number of current carrying conductors in a raceway, may require further ampacity adjustments beyond the parallel conductor adjustment. Always prioritize safety and consult with a qualified electrician if you have any doubts or complex scenarios. The NEC provides specific guidelines for directing conductors based on these conditions, and these adjustments must be applied in addition to the parallel conductor adjustment factor. For example, if the ambient temperature exceeds 30 degrees Celsius, you need to apply a temperature correction factor from Table 310.15 burn. Similarly, if you have more than 3 current carrying conductors in a raceway or cable, you must apply adjustment factors from Table 310.15b3. These tables provide specific factors based on the number of conductors. For 4 to 6 conductors, the adjustment factor is 0.8. For 7 to 9 conductors, it's 0.7. For 10 to 20 conductors, it drops to 0.5, and for 21 to 30 conductors, it's 0.45. Finally, for 31 to 40 conductors, the adjustment factor is 0.4. The order in which you apply these adjustment factors does not typically affect the final ampacity, but it is crucial to apply all applicable factors to ensure an accurate and safe calculation. Remember, these ampacity adjustments are cumulative. If you have multiple directing factors, such as temperature and number of conductors, you must multiply all the applicable factors together and apply the resulting overall factor to the conductor's ampacity. For instance, if you have a conductor with an initial ampacity of 100 amps, an ambient temperature correction factor of 0.9, and a conductor directing factor of 0.8, the final adjusted ampacity would be 100 amps multiplied by 0.9 multiplied by 0.8, which equals 72 amps. It's also important to consider voltage drop when sizing parallel conductors, especially over long distances. Voltage drop occurs due to the resistance of the conductors, causing a reduction in voltage at the load end. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, you may need to increase the conductor size beyond what is required for ampacity alone. When conductors are run in parallel, the voltage drop is reduced compared to a single conductor carrying the same total current. This is because the current is divided among the parallel conductors, reducing the current in each individual conductor and therefore reducing the voltage drop. However, it is still essential to calculate the voltage drop for the parallel conductor configuration to ensure that it remains within the recommended limit. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times the length of the conductor in feet times the current in amps times the impedance of the conductor in ohms per foot divided by 1000. The impedance of the conductor can be found in conductor property tables. When using this formula for parallel conductors, remember to divide the total current by the number of parallel conductors to determine the current in each individual conductor. Additionally, ensure that all parallel conductors are of the same material, size, and length. This is crucial for ensuring equal current sharing among the conductors. If the conductors are not identical, the current will not be evenly distributed, which can lead to overloading of some conductors and potentially hazardous situations. The NEC also requires that parallel conductors be arranged in a way that minimizes inductive reactance. This is typically achieved by placing the conductors close together and using a symmetrical configuration. For example, if you have 3-phase conductors and a neutral, you should arrange them in a triangular or square configuration to balance the inductive reactance. Proper termination of parallel conductors is also essential. Each conductor must be terminated in a separate terminal or connector that is rated for the conductor size and material. It is not permitted to combine multiple parallel conductors into a single terminal unless the terminal is specifically designed and listed for that purpose. When using multiple conductors in parallel, it is also important to consider the working space requirements around the electrical equipment. The NEC specifies minimum working clearances for electrical equipment based on the voltage and the location of the equipment. These working clearances must be maintained to ensure that workers have safe access to the equipment for maintenance and repairs. In some cases, using parallel conductors can increase the size of the equipment and therefore require larger working spaces. It's also crucial to properly identify and label all parallel conductors. Each conductor should be clearly marked with its size, material, and function. This will help ensure that workers can easily identify the conductors and avoid making mistakes during maintenance or repairs. In addition to the NEC requirements, local codes and regulations may also have specific requirements for parallel conductors. It's important to check with the local authorities to ensure that your installation complies with all applicable codes. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or electrician to ensure that your parallel conductor installation is safe and compliant with all applicable codes and regulations. Moreover, understanding this specific application and load characteristics is critical. For instance, where-to loads often require special considerations due to inrush currents during startup. The NEC provides guidance on sizing conductors for motor loads, taking into account the motor's full load current and starting current. In some cases, the conductor size may need to be increased to accommodate the inrush current, even if the continuous load is relatively low. Similarly, for nonlinear loads, such as those found in electronic equipment, harmonic currents can be a significant concern. Harmonic currents can cause overheating of conductors and equipment, as well as voltage distortion. To mitigate these effects, it may be necessary to use larger conductors or install harmonic filters. The NEC also addresses the use of parallel conductors in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust are present. In these locations, special precautions must be taken to prevent ignition of these substances. The NEC specifies requirements for the type of wiring methods and equipment that can be used in hazardous locations, including restrictions on the use of parallel conductors in some cases. Proper grounding and bonding of parallel conductors is also crucial for safety. Grounding provides a path for fault current to flow back to the source, which helps to trip over current devices and prevent electrical shock. Bonding ensures that all metal parts of the electrical system are at the same potential, which reduces the risk of electric shock. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors that must be used. When using parallel conductors, it is important to ensure that each conductor is properly grounded and bonded. This may require the use of additional grounding conductors or bonding jumpers. Furthermore, coordination with other electrical systems is essential. Parallel conductors should be coordinated with other electrical systems such as lighting, HVAC, and fire alarm systems to ensure that the overall system operates safely and reliably. This coordination should include considerations for load sharing, voltage drop, and fault current protection. In some cases, it may be necessary to install separate services or feeders for different types of loads to avoid interference or overloading. Also, the type of insulation used on the conductors can also affect their ampacity. Different insulation types have different temperature ratings which determine the maximum temperature that the conductor can withstand. The NEC specifies the allowable ampacities for different insulation types in Table 310.16. When selecting conductors for parallel installation, it is important to choose an insulation type that is suitable for the operating temperature of the conductors. In addition to the ampacity, voltage drop, and grounding requirements, it is also important to consider the mechanical protection of parallel conductors. Conductors must be protected from physical damage such as abrasion, impact, and crushing. The NEC specifies requirements for the type of raceways and enclosures that can be used to protect conductors. When using parallel conductors, it is important to ensure that the raceways and enclosures are large enough to accommodate all of the conductors and that they are properly supported. Remember, working with electricity can be dangerous. Always follow safe work practices and use appropriate personal protective equipment. If you are not qualified to work on electrical systems, consult with a licensed electrician. In summary, sizing parallel conductors involves several key steps. Firstly, determine the total load current. Secondly, apply any applicable directing factors for ambient temperature and the number of conductors in a raceway. Thirdly, calculate the minimum conductor size required to carry the adjusted current. Fourthly, consider voltage drop and increase the conductor size if necessary. Fifthly, ensure that all parallel conductors are of the same material, size, and length. Sixthly, properly terminate and label all conductors. Seventhly, coordinate with other electrical systems and consider the mechanical protection of the conductors. Finally, consult with a qualified electrical engineer or electrician to ensure that the installation is safe and compliant with all applicable codes and regulations. Keep in mind that this is a simplified overview, and the specific requirements for parallel conductor installations can vary depending on the application and the local codes. Always refer to the latest version of the NEC and consult with a qualified professional for detailed guidance. By following these steps and guidelines, you can ensure that your parallel conductor installation is safe, reliable, and compliant with all applicable codes and regulations.